what we call harmonic waves. They have this oscillatory behavior. We introduce the wavelength, which is the physical distance when you look in the space, in the physical domain in coordinates, the x along the x coordinate, that is the distance between 2 points of equal phase. So these points can be either minima or maxima. And then when you look in the time domain, the same distance in the time domain is called the period. The period is the inverse of the frequency, and the wavelength is related to beta, which is called the wave number. So lambda is the wavelength, and beta, which is 2 pi over lambda, is called the wave number. And we will see later that these wave numbers are extremely important, all right, as we will start solving problems. So that's what we have seen so far. The period, the wavelength, of course, the radial frequency, and the wave number. And at the end, we also derive the phase velocity, or the velocity of the wave, which is the radial frequency divided by the wave number. Okay, so now, as we talked last time, we are gonna try to figure out how to start solving problems which involve only one singular frequency of excitation. What I mean is, if here, now I'm gonna write, so move that. If we have now a circuit, let's assume that at this point we have a circuit with an AC source. We show it like that, all right? And let's assume, very simplistic, I will do this for a moment, that here we have a resistor, R, and here we have a capacitor or an inductor, all right? And then this is V. And let's assume that V creates a voltage. In fact, usually in the time domain, also, I need to tell you that we show that with lowercase, all right, in the time domain. And you will see the capital will be for the frequency domain. But let's assume that here, this is V naught cosine omega t, all right? So how would you solve this problem? How would you find the current that flows? All right, let's assume that we want to find the current. This is from circuits, all right? So you will use Kirchhoff's laws, and you will say, okay, this is V sub bar. This is gonna be C, let me put C on the other side. C here, V sub C. Let me put this one here, V sub L. So from Kirchhoff's law, we know that V equals V sub R plus V sub C plus V sub L, okay? How much is V sub R? Is R times I. How much is V sub C? Who is gonna tell me? We are time domain, see? Yeah. Okay. C is the inverse of resistance. That's what you need to remember. C is the inverse of resistance. So V sub L is going to be L di dt. All right. All right. So do you agree with that? Any disagreements? So then we you put that in here and creates an equation that looks like this. IR plus 1 over C I dt plus L di dt. So yeah, we have one unknown in the problem, but we have an integral and a derivative. And then how would you solve this problem if you wanted to get rid of the integral? You will take a second derivative, all right? So you will say dv dt will be r di dt plus c, 1 over c, sorry, 1 over c I plus L di d square I dt square. And you solve, therefore, a second order differential equation. And this second order differential equation, I will write it practically. L di square dt square plus R di dt plus 1 over ci equals dv dt. You know L, you know R, you know C, you know V. And then therefore you go and solve second order equation. All right, that's what you have when you have an LC. All right, well, what if I had 2 C's, C1, C2, and 4 L's? Then I would have a very high order differential equation. And who knows, I mean, we will have, who could solve a higher order differential equation when computers were not available? Even now, why would you have to go to a computer and solve those? I mean, the solutions are very complex. So then people say, okay, I have one thing here that V is a cosine of omega t. So then I can apply a transformation. And what is this transformation? It says that if I have a function of time, v of t, which is a continuous function, all right? It does not have, I mean, there are also that can apply for discontinuous functions, but cosine omega t is a continuous function. So we have a nice way to develop a transformation. And this is going to be 1 over t. Oh, excuse me. Sorry. If you have the, I will do this Fourier transform, then v of omega will be 1 over t f of t e to the minus j omega t dt. Okay, so I create this transformation. And why? Well, people knew about these kinds of transformations, all right? But why is this particular transformation very interesting for us? Because if your function here, your f of t, is a cosine function, what happens to, I'm not going to solve this integral here because it's going to, I mean, you can solve it easily, but do you want me to solve it? I will solve it for you. So here is, how much is cosine omega t? We have to plug in the cosine of omega t for a moment. I just want to remind you, have you seen this before in mathematics? Have you guys seen this before, you remember? Kind of. Okay, let me then do this. I was going to make a statement, but I will demonstrate it for you, so at least you remember it once, why we use it. Because there is a reason we use Fourier transforms to go to the frequency domain. Okay, so how do you write cosine omega t in terms of an exponential or exponentials? Do you remember? E to the j omega t plus e to the minus j omega t divided by 2. Remember that? Okay, so now I can plug in equation 1. I can plug in 2. And then what do I have? 1 plus 2. It gives me the following, that v of omega equals 1 over t. All right, and then I have cosine, I plug in for cosine of, later. Let me see here. E to the minus j omega t dt. And that gives me 1 over t cosine, oops, no, replace that with e to the j omega t plus e to the minus j omega t divided by 2 times e to the minus j omega t dt. And that gives me 1 over t. In fact, here is omega naught, all right? So I have to make that correction. This is the reason I'm doing that. I put omega naught in cosine is because omega is a variable inside the, all right, for this transformation, omega is a variable, but for us, the excitation has one particular frequency. All right, so omega naught, for example, is going to be 2 pi f naught, where f naught is the frequency of our source. So it has to be omega naught. So here, omega naught. Okay, to differentiate from the other omega. And then I have 2 here, and then it becomes j minus j omega minus omega naught t plus e to the minus j omega plus omega naught t dt. All right. Do you happen to know, or has somebody told you that this one here, what is this integral? One over 2t. That, of course, this implies from minus infinity to plus infinity, all right? Minus infinity to plus infinity. It's indefinite integral. All right, and then it's j minus j omega plus omega naught t dt. Okay, so now this one, that is in mathematics, we know that this integral e to the minus j omega minus omega naught t dt from minus infinity to plus infinity is what we call the delta function. Have you heard about this? Perfect. The delta function is a function here. If this is omega and this is 0, for example, and this is omega naught, the delta function is something like that. Is a function that has a value, an infinite value, but say 1 in our case, at one point. That's the delta function. All right, it has a value at one point only. So if we take this as the definition of the delta function, then this one here, which is equation 3, is giving us the following. So 3 will tell us that V of omega for omega naught here is going to be, I hope, yeah, sorry. Okay, V of omega is going to be 1 over 2t. And then here we have two delta functions, delta omega minus omega naught plus delta omega plus omega naught, which means if I assume that frequency is like a variable that goes from minus infinity to plus infinity, of course, there are no negative frequencies, all right? All of this is mathematical, but if we were assumed that this was a variable, so practically our cosine function in the frequency domain, our cosine of omega naught t in the frequency domain, which also we call the Fourier domain, because we apply the Fourier transform, has the following form. If this is 0, it's one delta here, at minus omega naught and another delta here at omega naught. But because we know that our frequencies are real, practically it's only this one that we're considering, all right? So what does that mean? That tells us that people knew from mathematics that if I have a harmonic excitation, harmonic, all right, in the frequency domain, it gives me only one frequency, omega naught. It becomes one frequency, all right? So from that point of view, they say that if I apply a Fourier transform to this, practically every cosine omega t is I can, for example, write that the cosine of omega t in the frequency domain is going to give me 1 point, which is going to be omega naught. I mean, if you want to consider it as the full spectrum gives you 2. So when I apply the Fourier transform to my differential equation, I get rid of all of the differentiations, all right? And then at the end, I get a different equation. So let me, in fact, try to do that. So I will do it in the following way. I will take the whole, I would summarize it. So the formula that we use to go from this circuit, after all of this, since we all understood that in frequency domain, that will give us only one frequency, not many, all right? Then we take this and we convert it. We have a conversion formula that we generate. And the conversion formula, so if I take this one again, copy, and I take it and paste it here, the conversion formula tells me that from time domain, time, and then so I want you to remember this table, time here, so frequency. All right. And this is only for harmonic excitations. All right. So we have T and we go to omega. Then when you have a V, which is V naught cosine of omega T, then we, in fact, let me write it here, V naught. Then for the frequency domain is going to be V naught. When we have R, in the frequency domain is going to be also R. When we have C, in the frequency domain is going to be 1 over j omega C. And it's going to be equivalent. So that's going to be resistive units, all right? L is going to be j omega L, where this one is in 1 over second. V naught is going to be in volts. R is going to be in ohms. 1 over j omega C is going to also be in ohms. And j omega L is going to be in ohms. So that is very interesting because still in this case, C is in farads. And still in this case, L is in henries. But when you place them on a circuit as 1 over j omega C, the 1 over j omega C is ohms. You need to remember that, okay? These are the units. Even if C is gonna be in farads and L is gonna be in henries, all right? So, and that's what you have seen And that's what you have seen in your circuit theory, isn't it? So practically the above circuit is going to take the following form. It's going to be, still consider it to be an AC source, but now we indicate it by V. We are going to have the resistor. You're going to have the capacitor. You're going to have the inductor. But now in this frequency domain, this is going to be R. This is going to be 1 over J omega C. This is going to be J omega L. This is going to be I, capital. And therefore, if I were to apply Kirchhoff's law in this one, here is what I would have. VR, VC, VL, and then I will have that V naught will be, VR first of all, is IR, V sub C will be 1 over J omega C I, V sub L will be J omega L I, and therefore V naught will be IR plus 1 over J omega C I plus J omega L I. Okay. Where V naught is the maximum of the initial voltage. All right. It's the maximum of the harmonic excitation. And when does the maximum happen? When cosine omega t becomes 1. So V naught is the maximum. And there I, whatever I you find from here, is going to be the maximum. I is going to still be a harmonic. All right. So I here, in this particular case, would be V naught over R plus 1 over J omega C plus J omega L. And this is still a harmonic function. And I will be, of course, the real value of I, in this particular case, will be the maximum, all right, of the real value of the current that is in the time domain circuit. So, but that's what you are going to have from this point on. From this point on, we're going to have, and as a matter of fact, is before I finish, is that from this point on, we're going to have the circuits that involve frequency. And in this particular case, in fact, I wanted to write it here for you, so you see it. This is going to have a magnitude, and eventually it's going to have a phase. All right, because it's a complex number. And of course, the phase is going to be a function of this particular frequency. All right, which is the frequency of the source. And so in these circuits, if you remember when you solved them, you said that the current and the voltage will be out of phase. Why is that? Because if I want to transform the circuit from what it is here to the real, to the time domain, I will of course get the real part of V naught, which is this, and that is going to give me V naught cosine omega t. But the way I do this primarily is I get the real part to find the V. So how do I go back from, let me rewrite it. How do I go back from frequency to time domain? So conversion from frequency to time. The conversion now, it happens as follows. Okay, so here you have frequency and here you have time. So in frequency, you have V naught. In time, V of t will be the real part of V naught e to the j omega t. That's the definition. And in fact, we call this V naught the phasor. So V naught is called the phasor form for the voltage. Okay, I of t will be the real part of the I that I found here. Let me call it I naught in this particular case. All right, I naught e to the j omega t. So in fact, I will come back to find this. Then of course, C is going to remain C. C is going to remain C. L is going to remain L in their locations. Where now V of t becomes V naught cosine omega t, exactly of what I had. And I of t in this circuit becomes the real part of I naught magnitude, in fact, I'm sorry, magnitude of I naught, magnitude of I naught, e to the j phi I, or let me go, yes, I, e to the j omega t. So what is the real part of this is I naught, and then cosine of omega t plus phi sub I. All right? And then you find it from here, the magnitude and the phase. Sorry. All right. Now, check this one. You remember those? You have seen those, all right? In circuit? Yes? No, good. I just want to make sure that we connect to what you have seen. Now, if you see here, that's the voltage. And if you see here, that's the current. What do you see? That the voltage and the current are out of phase. All right? And that happens always when you have reactive elements. So now we are going, since we've said that, and we have defined the Fourier transform, and we have defined the conversion back from omega to T naught. So now you need to remember these expressions here as the conversion. All right, you need to remember those. And also you will need to remember these transformations here. To take us from time to frequency and from frequency to time. In fact, maybe I can enlarge this. And now, having said that, we are ready to move and start looking at ways to transmit AC power that is excited by a harmonic source. And we will try to find ways to transmit this power from one point in place to another. And we will call the lines we are going to use to make that transmission lines. And there are a number of transmission lines, but here the ones that we are going to consider will be the microstrip line, the strip line, microstrip line, coplanar waveguide, and coaxial waveguide. And we're not going to solve them separately because we are going to look at their geometry. And then we are going, the book has a list of formulas that show you how the geometry translates into symbolic parameters that we use for the transmission lines. And then using these parameters, for example, how much is your R, how much is your C, how much is your L per unit length, Then we are gonna go and start working on transmission lines in their symbolic form. Because we always do that in circuit design, all right? We always try to go from geometries to symbolic representations, where we have defined how in these transformations from frequency to time are important to remember, because a lot of times we are going to be in frequency, but we are going to have to keep in mind that in reality, everything happens in time, all right, in the time domain. So this is also a second part of the introduction. This was important to bring together some things that you have seen with what we are going to use now. And then Monday, we're going to go and start looking at three-dimensional structures and see how in a macrostrip line, you use all of the information we got from statics to characterize it, to find a capacitance, all the information we used from magnetostatics to find the inductance, and then we're going to use an RLC symbolic representation for the transmission line, all right? And then we'll start solving problems there. So that's how we're going to go. Any questions? Okay, so we have office hours tomorrow. If you have any additional questions about the homework, please come to office hours. Okay, thank you.